Hello. So I'm going to talk, as Julia has said, about the project Sailfish. And this is a GPU-based ocean numerical model. So the first thing I want to tell you is what an ocean numerical model is. So basically, it is a program that simulates ocean circulation. So there are global ocean numerical models that simulate the behavior of the ocean in the Earth, but they don't have much resolution. We are interested in studying water quality issues near the coast, in the shelf area, and also in estuaries. And for that, we will need to know the circulation of the ocean with high resolution in the near coast areas. So the first thing that you have to do when you do this type of models, you have to discretize it. So we can solve the equations using a computer. So that means that we will define a 3D, in this case, it will be a 3D mesh. So here you see the horizontal part of it, and here you can see, this is a cartoon of the 3D mesh. In reality, we have more resolution, like 1000 by 1000. But the important thing is that we have to discretize the area of interest, and then the model at every time interval, it will solve a discretized version of the physical differential equations. And well, if you know something about differential equation, you will know that you need to know the boundary conditions. So in our case, will be lateral boundary conditions in the sea area on the coast, and then meteorological boundary conditions or forcings at the free surface. Okay, so why do we need numerical models for the ocean? What are they used for? So the big problem is that we don't have good observational data. So it is sparse in space and time. Even with satellite data, we can only measure some variables, temperature and free surface mainly. For example, we cannot measure the currents or the salinity. And we can only measure with satellites only at the surface, and only if there are no clouds. If there are clouds, which happens quite a lot, we cannot measure anything. We also have buoys and floats and other sensors in the ocean, but they only cover a very small part. So if we want to have a complete picture of what's going on, a 3D picture of all the currents and temperature and salinity on the ocean, we need to have a numerical model. And maybe most importantly, if we want to predict what is going to happen in the future, we need a numerical model. And this is very important for real operations. But currently we have models, but they have limitations. So probably the most important limitation is that these models are huge and they take a long time to develop. We are talking about decades, 15 years or 20. So their design reflects the time when they were started. So most of these models are written in Fortran and not a very modern dialect. So here I'm showing you an example of prompts. This is a model that we are trying to replicate. And you can see, for example, they use the old way of writing operators, which is not very clear. They don't use matrix operators. So they do all the loops, and they don't even use the best ordering to make use of the cache. So that makes this program very difficult to read, especially for modern programmers, and not very optimized because of the way that things are written. And an important point is that they use an MPI approach, which was the way of doing things in high performance computing at the time. And there are some implicit assumptions in MPI, and because initially there were like lots of small computers, implicitly we are assuming that each computer doesn't have a lot of memory, each of the cores, and that the CPU is the fastest way to do computations in a computer, which is not true nowadays. So the limitations, one of the limitations that we have found is that programs, the current models are much slower than they could be potentially. Source code is extremely long and complex. So the latest version of these ROMs models that we want to replicate is around 200,000 lines. Fortran, all Fortran is understood mainly by all people. And well, if we want to make a change to add more physics or something like that, it is very difficult. It is very difficult to scale these models to do something else. There is another limitation of current ocean numerical models, which is derived from the fact that they are slow. So I want to talk a little bit about the problem of nonlinear models like this. They are usually chaotic, meaning that even if we have almost perfect initial conditions and boundary conditions and equations, even if all that is perfect, we can have very different results by just changing those things slightly. For example, if you change the initial conditions slightly, you can still have a very different prediction. So imagine here that we are looking at a temperature at one point in the ocean in our forecasts, and we have started many forecasts with a slightly different initial conditions. So this is a picture of what we will have. So we will have a most probable, most likely result, but with a larger variation than the initial conditions. But then we'll also have some situations, let's call them extreme events, that happen from time to time, but they can be very important. Usually catastrophic events are extreme events, and they happen with low probability. So if we really want to do a good forecasting, we will need to run ensembles of runs, usually on the order of hundreds. So this is a big limitation nowadays. With the models that we have and the biggest computers that we have, we can run just few, maybe on the order of 30 and not of the order of hundreds. So we need to create models that are fast and efficient. And efficient, I'm talking about mainly about energy efficiency. We are trying to solve, in our case, to solve problems related to climate change. We don't want to increase the energy expenditure in the world. So we are trying to solve all these problems by making a new version of this numerical model ROMs, and we will base our program on it. And basing it means we will have the same inputs, produce the same outputs, and we are using the same algorithm. So we are not inventing a new things. We just want to have something that we can just substitute by the old one, but that can be potentially much faster. So we are writing it mostly in Python plus CUPY library, by adding also some C++ CUDA kernels in the parts that we need to be really fast. And we have designed it to fit in just one GPU and make all the calculations inside of the GPU. So this has the potential of being fast and efficient. So just to give you some context, the typical problems that we have has a mesh of 1000 by 1000 nodes in horizontal, and then around 10 nodes in the vertical dimension. So one 3D variable, like for example, the temperature that we have to store as double, takes approximately 100 megabytes. So if you take into account all the variables used at the peak, that is typically 10 gigabytes of memory. So it fits easily in one of the more advanced GPUs that have like 40 or even 80 gigabytes. It fits easily. We can even run several models in just one GPU. Also, so you have some context, the original ROMs, that is MPI, 25% of the time was spent only on MPI message passing. And this doesn't even take into account that the code that uses MPI is more complicated. So some things are also slower because of the additional complication. And yeah, our test shows that in a typical run of ROMs, adding more than 6 cores, running it in more than 6 cores is not really beneficial. So it has a poor scaling in terms of parallelism. So we have started our model, and we have replicated. There is a 2D component of the model, and this is the part that we have started, which is admittedly basic subset of ROMs, but it allows us to have an estimate. So running the same case using the 2D equations, shallow water equations, we can see that when you compare our GPU model with the CPU model, our model runs 1,500 times faster. I'm talking about one CPU only, so not really using MPI. So ROMs report that it spends more than 25% in that 2D kernel alone. We are talking about our GPU model runs hundreds of times faster than the CPU model. So we should expect big gains from our choice of using a full GPU approach. And then from the energy energy expenditure estimate, we have made a simulation using NVIDIA's simulator, and we are assuming that we have this AMD dual ROM CPU processor and the A100 SX M4 GPU, and we have found that the energy expenditure for one run is 10 times less or 11 times less in the GPU than in CPU. So you can see it as cost per floating point operation is 11 times less in the GPU. So we also should expect huge savings in energy. So the conclusions that we have extracted is that maybe nowadays MPI message passing interface is a less useful paradigm in high performance computing, especially for models whose memory fits into a single GPU card. And some people say that, well, there is no problem in just using both ideas. You can have MPI and GPU, but it's not really true because eventually you have to pass the memory from the GPU to the CPU. And well, there is additional complications by having two different approaches. So we believe that it is better if you focus in just one. And in our case, we have focused on GPU only. Sailfish is still at the first stages of development, but a preliminary estimates suggest that it can be much faster than CPU MPI based models like ROMs. And we are talking about 100 times faster maybe. And the energy savings can be substantial. And we are currently working on the 3D component of the model. So that will be like finishing 80% of ROMs, so we can better compare both and get better comparisons. Yeah, so this concludes the presentation, and